Hello, everyone. Thank you so much for being here. For those of you who don't know me, my name is Matt Brophy. I'm an English professor at the college and also the faculty fellow for college-wide reading. The college-wide reading program is set up so that we, across the college, students, faculty, staff, have a shared reading experience based around some important issue or theme in the world today. And our theme for this year is the current climate crisis. Our book, Under the Sky We Make by Kimberly Nicholas, is being taught in several classes on this campus and throughout the college. So many of you are probably already reading it in some of your classes, but if you haven't gotten the book yet or interested in it, touch base with me after this talk and I can get a copy for you. This is our last event for the fall, but we do have more events lined up for the spring. In particular, the author of the book herself is going to be joining us in February via Zoom. There is one more, not speaker event, but event going on for the fall, which is our fiction writing contest. So if any of you are storytellers, fiction writers, and are interested in that, I can share some information with you about that. We're accepting submissions until November 18th. So if you're interested and have a creative mind and idea about what the world might look like in one or several generations, I encourage you to write a story and participate in that contest. I'd like to thank the STEAM Speaker Series for co-sponsoring this event, the Downingtown Center staff for putting this space together and for getting us some refreshments for after the talk, George Dobbin for helping out with the Zoom and recording of this event, and all of you for being here today. Of course, I'd like to thank our special guest today, Professor Atsuhiro Muto, for making the trip out here to share his research. Dr. Muto is a glaciologist, a polar geophysicist, and an associate professor at Temple University. His research focuses on the history, present, and future of some of Earth's coldest places, such as Greenland and Antarctica, and how those places change as the climate continues to warm. He also teaches in the Department of Earth and Environmental Science at Temple, so those of you who are planning to transfer there, you might get a chance to study with him in the future. Dr. Muto's talk for today is titled Revealing the Deep Secrets, Geophysical Investigations of Subglacial Controls on the Antarctic Ice Sheet Stability. There will be time for Q&A after the presentation, so please make a mental note of anything you'd like to ask Dr. Muto as you listen. For those of you joining us via Zoom, please feel free to post questions in the chat. Join me all in welcoming Professor Atsuhiro Muto.
All right. Thank you very much. Thank you for the nice introduction, and thank you very much for the invitation to come out here. I live about an hour away, but I didn't have any reason to come out here, so it's really nice. I really like the campus, and this is a nice part of Pennsylvania. So, and the weather is great. So thank you very much. Okay. So what I'm going to talk about today is, I gave that sort of long title, but it's basically what I do, which is geophysical investigations of something beneath the ice sheet. But I'm going to actually focus on this one particular glacier called Thwaites Glacier and the ice shelf, which is a floating part of the ice sheet that is attached to the ice sheet. They're called the Thwaites Ice Shelf. So I'll spend about half the time talking about the research aspect, but I'm sure you're interested in how do you actually get there and what it's like to live there and actually do the research we do. So I'll spend about the other half of the time talking about those things and try to leave ample time for Q&A. Okay. So this is where you're looking at the Antarctic ice sheet. You have the South Pole right in the middle. Now, there's a bit that sticks out towards South America. That's called the Antarctic Peninsula. Then, I don't know if you can see, but at the top, you have the part that is closer to Africa, then part that's closer to Australia, but this Thwaites Glacier and Thwaites Ice Shelf, and if you zoom in a little bit, it kind of looks like this. Thwaites Glacier is about the size of the state of Florida. Okay? It has a lot of ice there, and it's been getting a lot of attention lately. And of course, we study it because of some reason. Okay? Now, you might have heard of this Doomsday Glacier, right? So I think it was actually this Rolling Stone magazine article that came several years ago that coined the term. And as scientists, we don't use it, okay? It's the media that came up with it, right? There might be some good reasons why you still want to call it Doomsday Glacier. We try to stay away, but the media keeps using it, okay? So those are just clippings of the articles that were published in as recent as September, but they still keep calling the Doomsday Glacier. Okay, I'll tell you a little bit of why that it might be Doomsday Glacier or why it's important and why we study it. Okay, now, and the big reason why is because the Antarctic ice sheet as a whole is losing ice. Okay, but they mostly happen around the coast. One of the ways we know that is using something called the laser altimetry, or satellite laser altimetry. It's just this fancy laser that is orbiting around the Earth, okay, and shooting down laser pulses. And you measure how long for the pulse to go down and come back to the satellite. And if you do that repeatedly, what you get is the measurement of the surface elevation, right? And of course, this kind of fancy thing, NASA is the only one who can do it. So it's a NASA satellite that kept going around, or keeps going around Antarctica, well, around the whole Earth, and measures the change in the elevation, right? And if you look at the data over some time, what you see is that around the coast of Antarctica, the elevation is going down, meaning the ice is being lost, okay? So in this particular figure, red is ice loss, blue is ice gain. So there are parts of Antarctica that's actually gaining ice, right? But you see clusters of red and intense or dense red. That means a lot of ice is being lost in some particular parts of the Antarctica, and it is called the West Antarctic Ice Sheet. Right? So roughly the Western Hemisphere, or the part of the Antarctic Ice Sheet that's in the Western Hemisphere. And if you actually look more closely, that's where this particular glacier that I was been saying, the Doomsday Glacier, Thwaites Glacier lies, where it's the red is most intense. That's where we're losing a lot of ice. Okay? So West Antarctic Ice Sheet as a whole is contributing about 0.3 inches, right? 7.5 millimeters of global sea level rise in the past, let's say roughly about 20 years. Okay. Of those 0.15 inches, right, or 3.7 millimeters, which is more than half of all the ice that's being lost from West Antarctica, comes from this particular glacier. Okay. And that is why some people might want to call it the Doomsday Glacier, and the potential for it to lose more in the future. Right? So West Antarctica as a whole, though, it actually has enough ice to raise the sea level by 10 feet, about 3 meters. Okay? I'm not saying that that's going to happen, and we are still trying to figure out if all that's going to be lost and how long it would take for that to be lost. Right? But the biggest thing about the biggest effect of losing ice from the Antarctic ice sheet is global sea level rise. So, this is actually something that you can get online and look at how the sea level rise is going to affect different parts of the world. Okay, so I'm just zooming in around Philadelphia, and with the 10 feet of sea level rise, we actually don't lose a whole lot, right? But things like Philadelphia International Airport, that's going to go under the water. A lot of New Jersey, not the coast, but the banks of the Delaware River is actually going to go under. Okay? So, but even if it's just losing Philadelphia International Airport, that's a huge deal, right? Because a lot of us fly out of there. It's a lot of money going there, and it's a very important infrastructure. What about just 2 feet? Okay, that's actually about the range of the sea level rise that we are actually talking about that could happen next 100 years, perhaps. And about 2 feet is the amount of ice in that Thwaites Glacier itself. Right? So again, we don't see a whole lot, but if you actually look at other places, right? 2 feet of sea level rise, okay, we're going to lose most of the Jersey Shore. I'm sure a lot of you do go to Jersey Shore during the summer, right? We're going to lose a lot of that. Okay? a lot of the New York, Long Island, and around DC and the Maryland coast, that's going to go under the water. So it is quite important to figure out even this one particular glacier, and if those 2 feet of sea level rise is going to happen and how fast it's going to happen. Right? You might think that we actually know it, but we don't. Right? There are a lot of uncertainties about how fast this is going to happen. It's going to happen at some point in the future. We know that. But is it a century? Is it 5 decades? Or is it 3 centuries? We don't know. So that's actually the kind of thing we're trying to figure out. Right? And we have this international collaboration called International Thwaites Glacier Collaboration. It's a very creative name, but it's a UK-US collaboration that's going on right now with several projects, basically doing whatever we could to study this particular glacier. I'm actually part of the 2 of them. And all these things called like Time, GHOST, Tarzan, those are the acronyms of the projects. And I'm part of this GHOST project and Tarzan projects. And what I'm going to talk about now is part of these projects. And I actually have one graduate student who just got to Antarctica as part of the GHOST project. She's down there. She's going to study what's happening to beneath the Antarctic ice sheet. But either way, the urgency of the problem and the importance of the Thwaites Glacier has made the UK and the US invest about $25 million to go on this project. And a small portion of that comes to Temple, and that's what I use. Okay. Now, so before going any further, I just want to go through what I call the anatomy of an ice sheet, right? So how it forms and how it behaves, right? So how it forms is, it starts as snow falling on land, and it's cold enough that the snow just keeps accumulating, okay? And it doesn't melt. It doesn't get warm enough in the summer for it to completely melt. So year after year, you get the snowfall, and under its own weight, it's going to start squeezing, okay? And thousands of years later, you're going to have this, the snow piling and squishing into ice, and you end up with this, what we call the ice sheet. That can be about a mile or 2, not 2 miles, but a mile or mile and a half thick at most, right? But once you accumulate that much ice, it actually starts flowing under its own weight. And some of that is going to go towards the coast. And once the ice goes off the coast, it becomes what we call an ice shelf. That's the floating part, the part that's floating over the ice, over the ocean. Okay. And there are some things like the ocean circulation, and the ocean itself can melt the ice shelf from beneath. And that's the kind of thing that we study intensely, and we want to figure out quite a bit, and how the ocean is actually affecting the behavior of the ice sheet. Okay. Because there can be some warm current, warm ocean water that is off the coast. Okay. Now, where that warm water comes from, I'm actually not really going to get into it myself, but part of that is global warming. But there's actually warm water that's circulating around Antarctica all the time. But how the ocean circulation and the air circulation around Antarctica is changing because of the climate change, that actually affects if this warm water is going to access the ocean, the Antarctic ice sheet or not. But things like the seamount, so the shape of the ocean bottom. So if you don't actually have the kind of seamount or the barrier for this warm water to get to the ice shelf and the ice sheet, all is good. But we don't actually know quite what the shape of the ocean looks like beneath the ice shelves, because you can't have the ship going there to measure the ocean bottom, right? So that's actually a big part of what I'm doing with one of these ITGC, International Thwaites Glacier Collaboration projects, right? Whether you have some barriers or not at the ocean bottom that could allow this warm water to access the ice sheet, right? And the way I do it is with the what we call the active source seismic surveys. I send down seismic pulses by detonating basically dynamite, and we look at the waves, seismic waves that reflect from the ocean bottom. Okay. So it works out as in the same way as the bats, how they navigate in dark, and also how the dolphins and whales use it's ultrasound, so different frequencies of sound, but they send out sound waves and they hear or they sense what comes back. And that's how submarines navigate in water. Okay, so same principle. Okay, so it's actually me doing that seismic survey, right? So yeah, sorry, I should have said that. Yeah, it's gonna go pop. So I'm actually a licensed blaster, so I'm allowed to transport dynamites or the explosives and set it off. Okay, so that's how I generate the seismic waves. Or if the ice is thin enough, you could actually do a hammer blow. So I'm just hitting a metal plate with a sledgehammer that I bought at Home Depot, my local Home Depot. Okay. Sometimes that's strong enough for the wave to go through the ice in the ocean and come back. Okay. Right. Now, so once you do that, and if you go around some of the ice shelves, you get some point measurements. And this figure is what this is showing is actually the blue and white is the shape of the ocean bottom on parts of Thwaites Glacier or the Thwaites Ice Shelf. Right. We have some idea of what it looked like before. Right. That's what you see in the background color, and you see the dots. But if you see the difference in the blue and the white, that's where I actually found the ocean to be deeper or shallower than what we knew before. And of course, there's a lot of subtlety in the ocean bottom that we didn't know about that could be affecting how the water is flowing beneath this ice shelf and have this kind of effect where the water is going to, how much of the water can actually get to the ice or not, is we're getting some new knowledge about that by doing this kind of seismic survey, right? So that's one part of what I did. Okay, so that's what I'm doing, and that is about what we call the ice-ocean interaction, so the interface between the ocean and the ice. Okay, but what about the ice that's actually sitting on land, right? So that's connected to what we call the ice shelf. So how does the ice on land, farther inland, respond to what's happening to the ocean is another part that I try to figure out. Okay? So what we call the subglacial geology, or what the ice is flowing over, whether it's hard bedrock, okay, or if it's like soft sediment, like sand or mud, okay, those things matter for how fast the ice can actually flow over land and get into the ocean and eventually melt away and raise the sea level. So what it comes down to is it made of hard rock? Is it made of sediments that can break, right? Those things matter hugely, but we actually don't know quite, its knowledge is quite well unknown. So that's another thing I do. What we call the bed, hard bed or soft bed. And it's another thing that the seismic survey can actually do, right? So I talked about sending the sound waves down and sensing for where the reflection of these sounds are coming from over the ocean, okay? But the other thing you can do is that those sound waves will penetrate through some sediment layers or different kinds of rock, okay? So you can figure out how thick they are. But what's cooler is if you send down certain sound, right? So I'm just putting in these wiggles down, okay? But depending on whether the bed of the ice sheet is hard or soft, what comes back is quite different. Okay, so let's say that what you send down sounds like wah wah wah. Okay, if it goes over soft bed, it goes wah wah wah. So the sequence of the sound actually flips. Okay, and for the hard bed though, for hard rock, it comes back as wah wah wah. I don't even know which one was the one that I sent down, but I think you get the idea that depending on the property of the bed or the material property, we get different kinds of reflections. And I use that kind of information to figure out where the bed is soft or hard, okay? So it's a kind of figure that I create from that kind of survey. So the top one with the purple and the green color, that's what the shape of the ice, the ice sheet or the Thwaites Glacier looks like. And the bottom figure, that's actually showing the strength of the bed, right? And from that, we can actually figure out what's hard versus soft. And we measure that against the strength of the ice. So basically, whether the ice gives to the bed or the bed gives to the ice, right? Does the ice actually break when they hit the hard rock, or is the ice stronger than what's beneath so that the ice is breaking the bed, right? So that's what I mean. One way we can see soft and hard bed, and you see these kinds of variability in where the bed is hard or soft. But what's important is that there are sections underneath Thwaites Glacier that is continuously what we call soft bed, continuously mud or sand that has a lot of water in it. And there are parts that have mix of hard rock and soft sediments, okay? And those kinds of things will matter for how the ice is flowing. But the only the data set we have is actually quite far inland, and it's actually the data that I'm showing is actually from where there's a green line that's only 40 kilometers long, right? And that is quite far away from the ocean, okay? That's like 200 kilometers inland of the current coast. So we are trying to collect a lot more data, right? And that's what my student is actually doing. She's going to conduct this kind of seismic survey, driving from inland all the way, well, not all the way towards the coast, because there are too many crevasses and you'll fall into crevasses if you go too close to the coast. So as far closer to the coast as they can go, they try to do that kind of seismic survey and figure out where the bed of the Thwaites Glacier is soft or hard, okay? And that would determine how fast the ice can flow into the ocean and respond to the changes happening to the coast, okay? Right, so I think that's enough for enough of the bulk of the science, I think. So I'm going to now switch my gear and talk about, first of all, how to get there. Okay. So what we do first is we fly to New Zealand, okay, a town called Christchurch, or city called Christchurch in the South Island, New Zealand. So to even get there, it actually takes like 24 hours. And that portion is commercial airline, right? So from Philadelphia, the last time I was there was 3 years ago. We flew to Houston, then there's 14-hour flight to Auckland, and we hop onto a smaller plane and go to Christchurch. And we spent a couple of days there in Christchurch, where they actually have this the warehouse of the clothing that we wear to go to Antarctica. It's called the Clothing Distribution Center, CDC, okay? Then we get on a plane, and from there on, it's actually the military plane, US Air Force, right? And actually the National Science Foundation, NSF, who's the people who are the people who fund us, they have a facility down there. So what it says is United States Antarctic Passenger Terminal. Okay, well, I try to make this thing go away, and I think someone has a question. Oh, maybe not, okay. All right. Right. Then we get on this, the plane. It's the C-17, it's a cargo plane, it's a cargo jet, and it takes about 5 hours from Christchurch to a station called McMurdo Station. That's the big logistical hub for the United States Antarctic program. That particular time, I hitched a ride with a huge front loader. There are about 100 passengers, or maybe 90-some passengers, and a huge front loader. So that plane is huge, okay? So it takes about 5 hours, and you land on the ice. They make a runway over the ice, so they sweep all the snow out so that the wheeled aircraft like this one can actually land. Okay? Then, when you're at McMurdo Station, right? I don't know if some of you have been to like Alaska. It kind of looks like that, right? You have these kind of buildings and a lot of dirt, not much green. Okay? That's what McMurdo Station is like, right? There are actually 3 bars, and there's an ATM, there's a post office kind of thing. But we spent 2 to 3 weeks there, gathering stuff that we send down from here, the scientific equipment. So those boxes, they all came from Temple, okay? And we gather those, and also we spend time getting some training for well, this is the crevasse rescue training. We have mountaineers that travel with us, right? So we're not the ones who, like mountaineers, or we're the adventurers ourselves. We're scientists. So we go with mountaineers. Some of the scientists are actually quite good at mountaineering, so they don't need their own mountaineers, but some of the things we do is crevasse rescue training, and after about 2 to 3 weeks, once we're ready, we actually fly to another place. And in this particular instance, there is another camp in the middle of the West Antarctic Ice Sheet called Waste Divide Camp, which is about 1,000 miles away from McMurdo Station. So we take another military plane, but slightly smaller, and the ones that have the, this time, ski. Because when you get to West Antarctica, there's no ice runway, right? And in this particular one, actually, National Science Foundation actually owns it, but the US Air Force operates it. Okay. Right. Then finally, there's a 320-mile leg from that camp to Thwaites Ice Shelf, which is where I was 3 years ago, right? Some of the planes so we get on a yet smaller plane and skied planes. Okay. So that's one kind of plane that we use. And I don't know, does anybody in the audience actually recognize that shape of that plane? Okay, so there's actually an interesting story with that particular plane. So if you look inside the plane, there's a serial number that you can find. Okay, so this one says factory number 4215034. I think that's what it says. Okay, you can Google this number and find out what the history of that plane is. And what I found is that this plane was manufactured in 1940, what does it say? 41 or 42, but it actually took part in the, why am I blanking? What happened on the French coast during the World War II? The landing of Normandy, actually. So this plane is really old. It's an old DC-3 that's being converted with turboprop engines. So they put new engines on, and they redid some of the shielding on the outside, but those DC-3 planes, they're actually quite popular in polar regions because of how strong the airframe is and how actually light they are compared to the how much cargo they can carry. So just some very interesting fact. And if you're an aviation geek, this would be something that, you drill over, but yeah, some interesting fact here. Okay. Sometimes we take another kind of plane, and another plane that's quite popular in polar regions. It's called Twin Otter. Okay. And that's when one of those planes came to pick us up. So we have all of our stuff, all our camping gear that's put on out on the ice shelf, but those things are all going to go on the plane. Okay. So we have skidoos or the snowmobiles and all the camping gear. Those things. It takes about 3 or 4 Twin Otter flights to get us all out. Okay. But this is what the camp looks like from the air. Okay. So we live in tents. That particular time, we actually had a tent each, so that was quite comfortable. But sometimes you pair up with other people. Right. So what we do when we're actually in the field is usually just drive around on these snowmobiles, and I go to different places, right? Then do that kind of seismic survey. But this is us commuting, basically, each day. Okay. It's a little loud, okay? So we fuel up, okay? Well, we have breakfast before doing this, but we have breakfast, put things on the sled, all the equipment that we need, and off we go. And we drive typically somewhere between 10 kilometers to sometimes 30 kilometers per day, going to different points for a seismic survey. And once we get to one point, what we do is we drill through the ice. Well, not through the ice, but to some depth of the ice shelf, about 6 meters, so 20 feet. Okay. We use a steam drill, so that's for drilling the hole for putting down the explosives. Okay. So there's a small steam chamber, and we just send down this steam so that you can melt through some layers of the snow and ice near the surface. Okay. And after that, this is the job for just a licensed blaster, where I would put together I've been saying dynamite. It's called PTEN, but that's the chemical, but it's actually a stable version of dynamite, or the TNT, sorry. And what you do is you put this detonator, that's where you put through the electrical charge, okay? So those green things, they're pretty stable on their own, but once they have a lot of shock, they will explode, right? So I'll put together the detonator and the explosive charge, and I lower it down into the hole. And then there's a wire that comes out. So for now, I'm tying it off, but in the end, what you do is you connect that to basically just a little box with batteries to put electrical charge through, and it will detonate the charge. And you've seen this one before, but here we go again. Okay. So that's how we do it. Okay, you've seen the data already, but this is actually how we do it in sequence. Okay. My colleagues at the same time were actually drilling through the ice and putting down instruments. So what we're doing is, and I'm helping my colleagues there is a hole that's already drilled through the ice going down to the ocean, right? So we're now putting down like fiber optic cables and also temperature sensors to get the data through the ocean. So how warm the ocean is, what the current is like down beneath the ice shelf. Those are the things that we want to know. And fiber optic cable is used for communication, but also how fast the light actually travels through the fiber optic cable is controlled by the temperature itself. So all along the fiber optic cable, you can actually measure the temperature. It's total magic. I don't actually do that myself, but it's a new technology that it's cool, and you can get a lot of good data. And on the surface, we have like solar panels, and there is actually a antenna for the what we call the iridium. So there's a satellite phone, so we can actually get the data sitting in our office. Okay, and this was 3 years ago, and they keep sending us data. And another crew is going back there to do the maintenance in a couple of weeks. But we sometimes leave these automatic, what we call weather stations, to make measurements. That particular time, there were, I think, 12 of us, right? That's 12? Yeah, that's the field party that we had, okay? So in some of the tents, it can get cramped, okay? So this is what the camp looks like, okay? And that particular tent is what we call the kitchen tent, okay? So that's where we come together and eat, okay? These boxes that we're sitting on or using as a table, those all contain food, packaged food, canned or foil packs, okay? Then we actually use common camping stove. So it is like camping, like you do around here, but just in quite different location, okay? Okay. So this is what it looks like. So I want to say that we're talking about science, but I don't know. I mean, I see boxes of wine there, so I think this might be some late night after a long hard day. Okay. And like I said, it's cramped. So when someone needs to move around, you have to stand up or retract your legs, and you just have to hope that you don't knock stuff off these tables. But so that's what it looks like when you're camping out on Thwaites Ice Shelf. Okay, and I think this is a video of me going to bed. So that's the toilet for boys. It's just a flag. Okay, that's where you pee. Okay, so I went to the bathroom. I'm walking into my tent. Okay, right. So They all look the same, so I have my temple flag on, and that looks like a door. And this kind of tent is called Scott tent. They're named after the kinds of tent that the Robert Scott, one of the famous explorers who unfortunately perished in Antarctica, but they used the same kind of tent more than 100 years ago, but it's been proven that this tent is the most resistant against wind and it doesn't let a lot of snow in. So the door is just cloth and you cinch it up. Okay? It's a little bit hard to get in and out, but that's because you want to block the wind and all the snow coming in. Okay? So once we get in, I can take my clothes off, but you have to close it off by tying a knot around that door. Okay? So I think it's actually 10 feet by 10 feet, so it's quite spacious. Okay? Because it retains all the heat that you produce, it does actually stay quite warm. We go down there when it's summer in Antarctica, right? So it's not too cold. I never go down there in winter. That's too cold. Right? So you see that I actually have 2 pairs of boots that I switch day to day because your feet actually sweat a lot when you're working. Okay? And you have good socks and lots of pairs of good socks and pairs of boots so that you can swap out each day so that you let them dry for a day and you can switch to the other boots the next day. That's the kind of how we live in Antarctica. And sometimes it's looks like this, all right? So all the photos that I have shown you previous to this one, okay, looked like it was kind of quite fun and didn't look like that, but there are some days when it's blowing, and this is sort of what we call marginal. We could work, but if the wind gets any stronger than that, we'll stop working. Okay? And that's our toilet, okay? So, yeah, see it shaking? So, you got to do your business pretty quick in that kind of weather. Okay. But, there are a lot of days when it's just calm and sunny. So after a hard day of work, we get out and I don't know, whatever is in my mug, hot chocolate, let's say, right? We enjoy ourselves down there. I've been to Antarctica 7 times and I really like it. So I keep going back. And of course, the science is important, but I think to be honest, I think that's probably the reason why I stay in this field, because I like working down there. So I think that's all I have for now. Okay. Maybe some of the important messages. Okay. So why do we study Thwaites and Thwaites Ice Shelf? I think is what it says. Because they're losing ice fast. Okay. And but we actually need more data to know exactly how much and how fast we're going to lose more ice and get more sea level rise from this particular glacier. Okay. So how do we get there? We fly there, but it takes many, many days to get there. And what is it like? Like I just said, it's kind of fun. And sometimes it's hard, right? And being away from home for quite a bit of time, that can be hard, but all in all, I think it's fun. So with that, there are some acknowledgements for the people who are funding us and people who work to help us down there. But I would like to spend the rest of the time taking questions and having conversations with you guys. So thank you for your attention. Okay. And I do see some questions here. So you can go almost any time of the year, but we choose to go when it's summer down there. So right about now is when the the summer starts, and until the end of January is basically when most of the scientists get out of there. Yeah. Yes. Yeah, so that was quite warm, just below freezing, I believe. It might have been that, so I usually use Celsius, so probably about -10 Celsius, or -5 to -10 Celsius. So some like 20 Fahrenheit, something like that, I think. There are some days when it's actually warm down in Antarctica than in Pennsylvania, right? Because it's winter here when we go down there. Yes. Yeah. Yeah. Okay. So there are many things that I didn't mention. That is definitely something we are doing. But they're expensive. That's one thing. And because they're expensive, they don't like to send them to a place that we don't really have a good idea about, right? So it's this thing of sending it little by little and extending the range. But what we really want to know is what's happening right where the ice sheet meets the ocean, where it's usually the farthest from the open ocean. So yeah, we definitely do that. And I'm actually off to this workshop down in DC right after this to talk about how better we can do this. So like over the next 3 days, we're going to try to come up with some cool new ideas or technology to do that better.
Because the elevation is dropping. How do you know it's not the land underneath subsiding? How do you know it's the ice now and not subsidence?
Right. Yeah. You can definitely tell who's like a geologist or I mean, you're a professor, so you know. We actually put GPS units on the, well, you can't really see, but there are some mountains or the rocks that are sticking out. Okay, so those are stable and the ice or the snow doesn't melt. Okay, so we measured how fast the land is subsiding or uplifting. Yeah, we do. Yeah. And in fact, though, you might be interested to know that Western Antarctica is rebounding the fastest on Earth right now. Some of that is, of course, from the ice melting currently, okay? But it just seems like the mantle down there beneath the Western Antarctic ice sheet is quite soft, so that the rebound rate is quite fast. Yeah.
One of the things that Dr. Nichols talks about is tipping points, point past which there's a certain degree of warming, like irreversible change starts to happen. Is there a danger or something like that in this area?
Yeah. So another point that I didn't go over is it's the configuration of the ice sheet, meaning what the bed topography of the ice looks like. Western Antarctic ice sheet, in particular Thwaites Glacier, has this particular configuration where there is a tipping point. And also, well, the modeling actually shows that we might have actually surpassed it, meaning that it has entered this mode of irreversible retreat is what we call it. Irreversible for several centuries to a millennial scale. Yeah, so yes, there is, and there's a chance that we've passed it already. But how fast, where it's going to go from here is we're still trying to figure out. Yeah, I saw one question there.
Excuse me. Thank you for your experience and the time coming. It looks so fearful as I look at it for me.
Yeah.
What I want to ask is, how long have you been visiting there?
Yeah, so the first time I went to Antarctica was 2003, so almost 20 years.
Okay, so doing your studies or doing your experience, have you heard of any accident? I don't know how to call it, kind of accident you guys experienced there. Has it been any time doing your experience or doing your studies where the sea just opened up or down there just opened up and then the ice went down melting?
So no, nothing like that in my time. But what I will say is that some of the changes that I've seen is where we can actually land the plane, so this kind of plane, they had to keep rebuilding the runway to further inland away from the ocean because it's actually getting warmer. And it's not all melting or the ice shelf is collapsing. It's that you get enough moisture on the surface so that it becomes slushy rather than just icy. So that the wheeled aircraft and all the skied aircraft, so they're harder to land closer to where the station was. So one thing that I didn't mention is that the airfield is about 1 hour drive away from the station itself. And that used to be a lot closer. Yeah. Not at McMurdo, but in different parts. So Waste Divide Camp, this place, that was actually made for ice core drilling. So I don't do that myself. I have colleagues who study that, yeah. And I think there was a question in chat. I think what it said was, so what is the prediction for the next 30 years, I believe? So we actually don't know yet. So I'm just giving the data and the results to what we call the ice sheet modelers now to see what's going to happen in the really, what we're interested in is the next century. But it's somewhere in the range of about 10 centimeters, or a third of a foot to 3 feet or something like that is the range that we're looking at for not the 30 years, maybe 50 to next 50 to 100 years of sea level rise. Yeah, so part of the global warming or the atmospheric warming is that warmer air can actually hold more moisture, right? Which means that you can actually have more precipitation. Okay, so you could actually, so where the mass, where it's blue, where the ice mass is being gained, there's actually more snowfall than what's exiting around the coast or melting. Okay, so a lot of East Antarctica, that seems to be the case. More snowfall. Right. Yes, yeah, and parts of West Antarctica, those are the places that's losing more than gaining. So more ice exiting the ice sheet than the snowfall, and the amount that's going out is so high that the precipitation is not catching up. Yeah. Probably not scary because I travel with mountaineers, so they keep us safe. But there are moments it's like, okay, you cannot go farther than 30 feet from where you are right now, which means that they think that there's something going on, well, we can actually see a lot of crevasses from satellite images, so they know that there are crevasses. So not really scary moments because the mountaineers are good. I think there's a question. Yeah. So when we drilled through the ice shelf and put down that instrument, I don't know where it is, we actually lowered the camera. So at the end of this, while we were doing this, we actually lowered the camera. We actually saw a squid swim by. Okay. And we also put hydrophones, so microphones down into the ocean. And I don't know if it's really right there or it was from far, but I think there were seals that we were hearing. Yeah, so there's life down beneath the ice shelf. Yeah. I am not sure because that's basically the first time we actually got to see or got any data from this particular ice shelf. So Yeah. Yes. That particular trip, it was mostly skua, so like big seagull looking things, and seagulls. Near the near McMurdo Station, you can see penguins, seals, sometimes orcas. They come around. Yeah, yeah, but I don't study them. Yeah. Okay. Yeah. Thank you so much for listening. Thank you. Oh. So Elias, right, online, yeah, we do actually use small submarines to investigate under the ice shelf, not the ice sheet. So that's the floating portion of the ice. Sorry, I didn't catch this one. Yeah. Okay, thank you.